And we're going to talk about the second order differential equation. Okay, second order differential equation. Okay, then what is the second order differential equation? Second, that means I have second derivative and only second derivative. We don't have more higher order derivatives. Okay, so here this equals 0. The function including x, y, x prime, y prime, that's 0. And for the function phi, here I have a function phi. If this phi having the property that satisfy this equation, then we call that this is the solution of the equation. The phi is the solution of this equation. If I have a second order, say probably y double prime plus y prime plus 3y equals 4, then I have a phi this function. When I bring this and it satisfies this equation, this phi is the solution. Okay, for example, here is the phi, and here is the second order differential equation. When it brings back, they still satisfy this equation, also with these initial conditions, then the phi is the solution. Also, another example, the phi is 1 over x squared. This is a solution for this differential equation, xy double prime plus 3xy prime equals 0. You can verify it. We will say this solution is phi. Okay. Within there's no initial conditions, but yeah, this satisfies this homogeneous second order differential equation. Okay. So now, again, that for the second order differential equation, we also need to know some types. First is like linear second ordinary differential equation. What is linear second differential equation? I have the equation form: y double prime plus px of times y prime, and the function of x times y equals a function of x. For this px, qx, this is a function of x, and we call this function coefficient function. And the f is called forcing function. Okay. We may have initial condition, and here you can see the initial conditions. It's not just one, we have two, because we may have two, well, since it's second derivatives, you may have two constants when you take the integration, right? So you need two initial conditions to determine your two constants. Okay? So for example, like here, this is our equation, okay, differential equation. Then y double prime equals 12x. When you take the integration, you get y prime only. And here is 6x squared plus c. And then you take the integration again. So that's why you have a c and k, these two constants. Okay? So here we have two parameters. Two parameters, c, k, and this c, k are independent. They won't affect each other. And then using the initial condition, first y of 0 equals 3. Then we can get k. K is 3. And then your y is 2x cubed plus cx plus 3. And the initial condition y of 0 equals 3, that means I have a curve. Okay, so finally the solution, that's a curve. So this curve will pass through 0, 3. Then how about C? We can use a second initial condition, y prime of 0 equals 1. Then you will get C equals minus 1. And finally your solution becomes 2x cubed minus x plus 3. And what does that mean? That my initial condition y prime of 0 equals 1. When we take the derivative, remember in calculus, it is called a slope. Okay, this slope is minus 1. Minus 1 at x equals 0. Okay. Then you may ask, how do I know that the solution I found is unique? And how do I know that I have a solution for this ordinary differential equation? So here is the existence and uniqueness. Okay, if I have a function p, q, and f, they are continuous on an open interval, and x naught is in this open interval, and also a and b are any numbers, then y double prime plus px y prime plus qx y is f of x. This linear second order differential equation with the initial conditions x naught, y of x naught is a, and when we take the derivative, which is a slope, y prime of x naught is b. In this case, we have a unique solution. So in this open interval, we have unique solution. Okay. So next, before we try to find a solution, in this case, we need to learn what is linear dependent and also linear independent, because we will use this concept to make sure that in the future, my solutions are unique. So what does that mean, linear dependent? I have two functions, f and g. We call they are linear dependent if the function of x is a multiple of function of g for all the x in that open interval I. Or the other way around, the function of x, g, is a multiple of function of x. Okay. And then what is linear independent? Here is dependent. Independent is just you cannot find the multiple of other function. So two functions they are linear independent if neither one is a constant multiple of the other. Which means that for those two functions, I cannot find a multiple constant. Actually, they shouldn't be equal. Okay. I cannot find the constant multiple of the other functions to satisfy that equation. Then they call linear independent. Okay. All right. Next, remember that we have coefficient functions and also forcing functions. So now for the forcing function, we just let it be zero. Then it is a homogeneous ordinary differential equation. Okay, so when f is 0, we call homogeneous for this differential equation. And then for this equation, I have two solutions, y1 and y2. And we have y1 and y2. And also the combination of y1 and y2, which means c1 y1 times a constant times plus the constant c2 times y2 is also a solution. Okay? Now we can quickly prove that, because since we say that the combination of the y1 and y2 is a solution, that means my y is c1 y1 plus c2 y2. Then why not just bring it back to this original differential equation and see if it is 0. So here we have y double prime plus function of x px times y prime plus q of x times y, and again your y is c1 y1 plus c2 y2. Then this becomes, let's just rearrange that, c1, and we have y1 double prime plus px y1 prime plus qx y1. And also, if we put everything related to C2, we have y2 double prime plus px y2 prime plus qx y2. Okay, so first term, zero, right? Second term, also equals 0. All right? Then we have C1 0, C2 times 0, and we get 0. So now, from this theory, if we know that y1 is a solution, y2 is also a solution, then the linear combination of these two solutions is also the solution of the differential equation. Okay. Right, next, let's see. Suppose I tell you that e to the 2x is a solution of y double prime minus y 4y equals 0, this differential equation. And also e to the minus 2x is also the solution. We will learn how do we find the solution later, maybe today or Wednesday. But since I tell you that these two are the solutions of this differential equation, that means the linear combination of these two functions is also a solution. Okay. Then you know that the linear combination of the two solutions is also a solution. And here we have the fundamental set of the solution. We said that two solutions, y1 and y2, they are linear independent in the homogeneous, which means the forcing function equals 0, linear differential equation. And they are said to form the fundamental set of solution. Okay, which means the linear combination of these two solutions is the fundamental set of solution. For example, y double prime plus y equals 0. Can you guess the solution? Again, that, as I said in the beginning of the class, we try to find a solution, and most of the time we guess. Okay, but in this case, can you guess the solution? Any thoughts? Using your basic knowledge. 0? 0 is a trivia. Yes. Cosine, yeah, the sinusoidal waves, right? Cosine or sine will be the solution, because suppose cosine x. If we do the derivative, we get what? Minus sine x. And one more, minus cosine. So minus cosine plus cosine equals 0. Okay? We will also learn how do we find a solution later. But so far, y1 is, suppose y1 is cosine. And of course, if sine function, when we have sine function, bring it back to this differential equation, that also satisfied. Okay, and these two functions are independent, or these two solutions are independent. Then we can say that the linear combination of these two solutions is the solution. How do we know that they are independent? Suppose this is fx and this is g of x. Can I find the constant multiple of the other one? One is cosine x and sine x. Can I times like 4, 5, minus 2, a constant multiple that should be equal? Impossible, right? Because they are perpendicular. Okay, so they are independent. And we say linear independent. Okay? But how do we know that they are two independent functions? Here we have a test. It's called Wronskian Test. So here, Wronskian Test is that I have a w, this function, and I turn the determinant. Okay. And when I turn the determinant, the first row is the solution, and the second row is the first derivative. So this is the solution. The second one is the first derivative. And then since we construct this W, that's called like a for Wronskian test, then if this is not zero, if and only if y1 and y2 are linear independent. Okay, so since it is not equal to zero, then we can say that two functions are linear independent. So here we have y1 and y2 are linear independent for all x in the open interval I. So let's use this Wronskian test to our previous example to see if these two functions are really independent or not. So we know y1 is just say cosine, and y2, let's say sine. And then here is our w. We have a cosine x, sine x. Okay. y1 prom. y1 prom just boom. We get minus sine x. y2 prom become cosine x. Okay. This is 1, right? Cosine squared plus 1, sine squared equals 1. Not 0 for all x. Then y1 and y2 are linear independent, and we can say that the solution is the linear combination of your y1 and y2. And to determine the constant C1 and C2, if we have initial conditions, say x equals pi and then y equals 3. And for the slope, at pi, that's 2. You will get C1 is minus 3 and C2 is minus 2. So the y is minus 3 cosine x minus 2 sine x. Okay. Any questions for this? All right, let's see another example. So here, forcing function is 0, that's homogeneous equation. We will learn how do we find a solution. But now I just give you two possible solutions, then ask you if they are linear independent or not. So suppose y1 is e to the 3x, and y2 is e to the minus 3x. And for the x, all of the x is real line. Let's put here. Let's see this w. We have e to the 3x, that's y1, y2, and the first derivative of y1, 3 times e to the 3x. And for y2, minus 3 times e to the minus 3x. That's minus 6, okay? Not 0 for all x. So that means y1 and y2 can form a fundamental set of solution. Okay. Any questions about this Wronskian test? Okay, now let's see next. For the homogeneous or non-homogeneous, if fx is not 0, then how do we find the solution? Or how do we do the solution? Here, I still have y1 and y2, and we say they are linear independent solution. For the homogeneous equation, you see, here is homogeneous. And also I have a yp. That is the solution for non-homogeneous. You can see I have f of x. So I have 3, okay, y1, y2 for the homogeneous solution. Yp, we will call particular p, is the solution for the non-homogeneous equation. Then I will say there's a phi. Phi is a solution. And this solution is the linear combination of your homogeneous solution plus the particular solution. Remember, when we talk about the first order differential equation, and if the equation is exact, then what do? We try to find the potential function, right? And then potential function equals C is a solution. Okay, but here, this, even though we have the same notation, different concept, we just say that this phi is a solution, okay? Because this phi is the linear combination of your homogeneous solution plus particular solution, okay? You don't need to equal to C. That's different concept, okay? We just use the same notation, all right? So this phi, that will be the complementary function plus any particular solution. Any particular solution means yp. And then this function means the linear combination of your homogeneous solution, y1 and y2. Okay? Okay, so now suppose we say that this particular solution is a solution of this higher order differential equation. What is my general solution? We also tell you that the homogeneous or complementary function is C1. Since it's, I take the derivative 3 times, it's a third order. So I have C1 e to the x, C2 e to the 2x, and C3. So 3 constant. If I say that this is the general solution of the homogeneous equation, differential equation, y triple prime minus 6y double prime plus 11y prime minus 6y, here that's equal to 0. This is the general solution or homogeneous solution for this third order differential equation. Then if I have a forcing term, 3x, the general solution becomes of y triple prime minus 6y double prime plus 11y prime minus 6y. Here we have equals 3x. That solution is your homogeneous solution plus your particular solution. Next one is the superposition principle. Okay, so suppose you can see here, for the homogeneous term, if I put O here 0, they are the same. Okay? I just have a different forcing function. With different forcing function, I have a different particular solution. We will also learn how do we find this particular solution with a different forcing function at the end of this chapter. But since I tell you that, okay, for this case with forcing function f1, I have this particular solution. Forcing function f2, I have particular solution p2. And also for forcing function f3, I have a particular solution p3. Then I will say if y is y, if I collect all the particular solutions together, this will be a solution. Okay, this should be what? Minus 4x squared plus e to the 2x plus x e to the x. This is also a solution. A solution of what? A solution of your homogeneous equation, and the forcing function will combine that. Okay, so I will combine all the forcing function to have another big or new forcing function. Then the particular solution will also the sum of the individual particular solutions. That's called superposition principle. Okay, and that will be also easier for you to analyze and find a particular solution. If you have this whole bunch together, how did you guess? Actually, with different forcing function, we also guess the particular solution. Okay, we will learn how to guess. Any questions? Okay, now with those basic knowledge, finally we can learn how do we find a solution. Okay, so first one we need to learn is the reduction of order. If I have a homogeneous linear second order differential equation, then I also tell you one solution, y1. Based on this solution y1, we can find the other solution y2. Okay, and here the other solution, our guess is that a function of x times your first solution. And remember that this ux is not a constant function. Okay, obviously, if it is a constant, these two functions are linear dependent, right? If they are linear dependent, then they cannot form a fundamental set of solution. Okay, so this cannot be the constant. Here is a non-constant function. Okay, if you find this is a constant, then actually you don't find any other solution and away. Okay, so here we assume that this is a u of x. And then since it is u of x, these two functions, y1 and y2, are linearly independent. They can form the fundamental set of solution of this second order differential equation. Okay? So with y1 and y2, the general solution is y is equal to c1 y1, linear combination of y1 and y2. That means c1 y1 and y2 is u of x, y1. Okay. Now let's find y2. Since y2 is u times y1, bring this back, okay. Then first we can find y2 is a solution. So y2 double prom plus py2 prom plus qy2 is 0. What is y2 prom? What is y2 double prom? Let's see. y2 prom will be chain rule. Take the first derivative, take the first term derivative, keep the second term, and plus keep the first term, take the derivative of the second term. And y2 double prom, do that again. So here we have u prom y1, that becomes u double prom y1 plus u prom y1 prom. And for the second term, we have u prom y1 prom plus u y1 double prom. So this is y2. And this is y2 prom, double prom. This is y2 prom. Okay. Now, the equation 1, since we bring the y2 here, the equation 1 becomes this is y2 double prom. And here is y2 prom. Okay. Let's also rearrange that. Okay. Let's rearrange. Since we have u double prom and u, so we put everything related, combined with u double prom here, and everything related to u here. And you can see that for this, what is this equation? y1 double prom plus p times y1 prom plus q times y1. 0, because y is the solution. So that's 0. Then this is 0. We only have this term, okay? And we divide by y1. So I have u double prom plus something times u prom equals 0. Okay? Since this is 0. Now we can change the variable. Okay, with that v equals u prom. So this is v. This is v prom. Right? So we have v prom equals u double prom. So let's rewrite that. We have v prom plus two y1 prom plus p times y1 divided by y1. V equals 0. Now you can see that that's why we call reduction of order, because here we have a first order, okay, So this becomes the first order. And we'll let this bunch of stuff as g of x. So we have v prom plus g of x v equals 0. Since this is a first order differential equation, what type of this ordinary differential equation? We have a three regular one and also another 3 special one. So what is the type of this differential equation? It's separable or linear, right? So you can see, let's put everything related to v on the left hand side and others on the right hand side. So we have v equals exponential minus p of x g of x dx. And remember, what is v? V is u prom, right? So u prom equals here, then what is u? Therefore, your u will be the integration of your v, which is e to the minus g of x dx, and then dx. This is e to the, what is g? G is 2y1 prom plus px times y1 divided by y1 dx. Oh, then we find the u. So the second solution, y2, that's u times y1. There'll be y1 times this bunch of stuff. Do we need to remember this? Memorize this formula? Actually, you don't, right? You just know the concept. What is the reduction of order? Since we know one solution, then the other solution, y2, will be u times y1. And your goal is to find u2. That's it. So you bring this back to your original differential equation and take the derivative and find u. Okay? Any questions so far? We will do 2 or even 2 examples, so you will see that how do we find u. Okay. Let's just see a real example, then you know that how do we use the reduction of order. Okay. So first, I have a constant lambda. Okay, I want to find this homogeneous differential equation. And suppose we know that e to the lambda x is a solution. Then let's try to find the other solution, y2. So suppose we know y1 is e to the lambda x. That is one solution. Let's find the other solution. So now at least we have a hint, okay? We know y1, the solution is e to the lambda x. Then for y2, the y2 is a function of x times y1, which is ux times e to the lambda x. Then let's see what is y2 prom and y2 double prom. Okay, for the side note, y2 prom is u prom e to the lambda x plus u lambda e to the lambda x and y2 double prom will be u double prom e to the lambda x plus 2 lambda u prom e to the lambda x and then lambda square u e to the lambda x. And green. Okay, now bring it back to the original equation. First, just write down again y2 double prom minus 2 lambda y2 prom plus lambda square y2 equals 0. What is y2 double prom? U double prom e to the lambda x plus 2 lambda u prom e to the lambda x plus lambda square u e to the lambda x. Okay, that's the green one. Now, minus 2 lambda, y2 prom, u prom e to the u prom e to the lambda x plus u lambda e to the lambda x. This is the blue one. Okay, y2 prom plus lambda square u e to the lambda lambda x. Okay. Now rearrange this. You see that it looks like we have a bunch of stuff, but we will definitely find something equals to 0. And here you'll get u double prom e to the lambda x equals 0. That's so easy. You get u is c1x plus c2. Right. Then the other solution, y2, will be c1x plus c2 times y1 e to the lambda x. We have c1x e to the lambda x plus c2 e to the lambda x. Now here you can see that the y2, we have two terms. And we also have e to the lambda x. This is y1, okay? And that times c2, like a constant. We can just let this constant 0 be 0 because this is already the solution. So with that, c2 equals 0 because e to the lambda x is solution. Then that's redundant. Okay, I only need this part. So the solution y is c1 y1 times plus c2 y2 . Okay. But are you sure that this is the C2? And also the linear combination of y1, y2 is really the fundamental set of a solution? Are they really linear independent? We don't know that, but we just learned the Wronskian test. So let's check the W. You have y1, y2, and y1 prime, y2 prime. That gives you e to the lambda x and y2 x times e to the lambda x, y1 prime x times e to the lambda x, y2 prime e to the lambda x plus lambda x e to the lambda x. This gives you e to the lambda x squared. It is definitely not 0. So y1 and y2 are linear independent.
Professor,
Yeah.
I'd like to ask why u double prime e to the lambda x equals 0 and why u equals c1x plus c2.
First, from here to here, that's easier. Why u double prime equals 0, right? U prime equals c1x. U equals c1. Oh, no. U prime equals c. U equals c1x plus c2. Right. And y from here to here? Now let's rearrange. U double prime, I have e to the x. That's it. Then u prime. U prime, what do we have? U prime, we have 2 lambda e to the lambda x minus 2 lambda e to the lambda x. That's 0, right? So this term, I'll cancel it. Okay, no 2 terms. And then here we have 2 lambda squared u e to the lambda x. Okay? And now minus here, minus 2 lambda squared u e to the lambda x. So they all cancel out. So I only have the first term equals 0. Okay? Yeah. So you can see that for the theoretical derivation, it looks like we have a lot of things to do. Okay, especially once you have your linear ordinary differential equation, and then you need to find your u, and then back to v prime. Looks like pretty complicated, but if you apply that concept to the real problem, sometimes they cancel out a lot. Easier to find your u. Okay, and in this case, we don't even have the changing variables, right? Because u prime equals 0. That's quite easy to get u. If you have u double prime plus something u equals 0, then u prime, then we may change the variables to v and v prime and v. Okay, depends on your questions. And let's see another example. You will know that how do we use the reduction of order. But before that, any other questions for this? Okay, so now for this differential equation, I tell you that one solution is y1 equals x squared. Maybe this time I can give you, just try it. Just 3 minutes. Okay, you try it to see if you can find the other solution, y2, or even just the order differential equation about u. Okay, let's go. So we know we need to assume that your y2 equals the u times x squared. Then do the derivation. Okay, find the y2 prime, y2 double prime, bring it back to the differential equation and simplify that. So make sure that we are on the same page. So let me give you, hopefully that you know, y2 prime should be u prime x squared plus 2ux. And u double prime, y2 double prime equals u double prime x squared plus 4u prime x plus 2u. And hopefully that you bring this y2 back to the original differential equation and you get the correct form. It should be u prime double prime x squared plus 4u prime x plus 2u minus 3 over x u prime x squared plus 2ux plus 4 over x cubed x squared u x squared. Equals 0. So the next step is important. How do you simplify that? Just be careful. A lot of things can be cancelled out. Then you should get x squared u double prime plus x u prime equals 0. Okay, is everyone on the same page to here? Because now we are going to find u. Okay, and since the question said that x is greater than 0, so how do we find u? X squared u double prime. Sometimes we don't even need change of variables, right? Because depends on the equation. So in this case, don't you think this is familiar? That well, actually, I can, since x is greater than 0, not 0, so we can cancel 1. Divide by x. Then we have x u prime overall to take the derivative. So we have chain rule. That's why we have the first term and the second term. Then x u prime equals constant. Your u prime equals 1 over x times the constant c. So your u is c times natural log x plus another constant k. Okay, now we can choose these two variables, two constants. Let's choose k equals 0 and c equals 1. So y2 is x squared natural log of x. Now we need to confirm, okay, make sure that y1 and y2 are linear independent. Then those two solutions will be the fundamental set of solutions. Okay, so to check if they are linear independent or not, then use the Wronskian test again. X squared natural log x. And take the derivative, we get 2x. The second term, 2x natural log x. The chain rule, so plus x. This one is x cubed, not 0. So y1 and y2 are linear independent. You know that how do you find the determinant, right? You times the terms diagonally and minus the off diagonal. Okay? So it'll be AD minus BC. Any questions for this? If you don't have any questions, then finally we are going to learn how do we find a solution for first the homogeneous linear differential equation. And for this homogeneous linear differential equation with constant coefficient. Constant coefficient, that means in the past this is the px and qx, right? So now it becomes constant coefficient, just a and b. And since it is homogeneous, no forcing function or forcing term. How do we find the solution? Again, now we guess. We always guess. So do you know that any equation, when you take the derivative, it becomes still itself again and again, and then you can cancel that. Like exponential function, right? Exponential function, if y is exponential function, e to the x, y prime is still e to the x, y double prime is still e to the x. Then I can cancel this exponential function. Then I try to find a and b. Okay. Well, not try to find a and b. That will satisfy this equation because we know a and b. All right. So one way is we can guess the solution is exponential, but it's not e to the x. It's e to the lambda x, and lambda could be varied. So in this case, What is y prom? Y prom is lambda times e to the lambda x. And y double prom is lambda square e to the lambda x. Then, so y double prom is lambda square e to the lambda x plus a y prom lambda times e to the lambda x minus plus by, so b times e to the lambda x, that's equal to 0. Then you can cancel the e to the lambda x. You get lambda square plus a lambda plus b, that's equal to 0. And we call this equation is characteristic equation. We need to find lambda. And once we find the lambda, that's our solution. Okay, and you can see that since it is quadratic equation, then we have two answers. Then that's why we have y1 and y2, because we have two lambdas, different lambda, then we have y1 and y2. But what is lambda? Okay, with this characteristic equation, we can find the root, okay, for this characteristic equation. The lambda should be arithmetic, okay, from your junior high. Minus a plus or minus the square root of a squared minus 4b divided by 2. Okay? And since we have the form for this root with a plus and minus sign, this root could be real and distinct, could be repeated if this is 0, or could be complex if the square root is negative. Okay, so we have three cases. So we may have real and distinct, repeated, and also complex. Let's see the first one. What does that mean, real and distinct? That means in the square root, that part is greater than 0. Okay, if a squared minus 4b is greater than 0, then I have lambda 1 and lambda 2, okay, because I have a plus and also minus. And suppose they are a and b, then my solution will be e to the ax and also e to the bx. We can also check if they are linear independent or not. So first, check their linearity. We have y1, y2, y1 prom, y2 prom. You get b minus a e to the a minus b x. Is that 0? Since we said that the roots are real and distinct, and roots are a and b, so I cannot get b minus a equals 0 because b is not equal to a. So this is not 0, and also b is not equal to a. Since the roots are distinct, so the y1 and y2 are linearly independent, then the general solution y will be c1 y1 plus c2 y2 okay. That is the first case if the roots are different. So here let's see this example. Y double prime minus y prime plus minus 6y equals 0. We guess the solution y should be e to the lambda x. Okay, and then bring this to the equation. You will get the characteristic function or characteristic equation is lambda squared minus lambda minus 6 equals 0. And you can see that the roots, we'll say real roots, the real roots are minus 2 and 3. So the general solution the y is c1 e to the lambda x minus 2x plus c2 e to the lambda x. Here the lambda 2 is 3x. Okay. Let's see case 2. I have repeated root, which means a squared minus 4b is 0. So my repeated root will be minus a over 2. Okay, so the root is minus a over 2. Then, well, we should have two roots and two solutions, right? So since here I only have one, that just means this is y1. Suppose that y1 is e to the minus ax over 2. And how can I find the other solution? We just done the reduction of order, right? So we can using reduction of order you can do it by yourself. Then we get the other solution is x times y1. Okay, your u will be the u times y1, right? U will be x and then y1 here. So the general solution will be c1 e to the minus ax divided by 2 plus c2 y2, you have x e to the minus ax over 2. If your roots are repeated. Okay. Here is an example. Y double prime minus 4y prime plus 4y equals 0. And you can, again, you guess the solution is e to the lambda x. Then you get the characteristic equation lambda squared minus 4 lambda plus 4 equals 0. And your root is just 2. So your solution C1 y1, and the other solution I will generate x times y1. Okay. So if you have a repeat root, then the second solution is just times x. Last one, more complicated one, since now a squared minus 4b is less than 0, then we have a complex root. So for complex root, your root will be like p plus iq or p minus iq. And in this case, p means p is minus a over 2. And also q is a squared minus 4b. Okay. And since those two rules are different, distinct, so my solution is just C1, Y1. Your Y is e to the p plus iq x. And the other one is p minus iq x. Okay, that's your general solution. So here is the example. Okay, the characteristic equation is lambda squared plus 2 lambda plus 6 equals 0. And the lambda is minus 1 plus minus square root of 5i. So we have the general solution C1 e to the minus 1 plus square root of 5i x plus C2 e to the minus 1 minus square root of 5i x. Okay. But since here the homogeneous equation and the coefficient is real number, and finally I give the answer as a complex number, it's a little bit weird. Okay, so we can also simplify this expression, the solution. So if we use the Euler's formula, let's see what is the Euler's formula. Euler's formula, e to the ix is cosine x plus I sine x. So if I change all the complex exponential to cosine and sine, then first y1 is e to the p plus iq x. So I have e to the px times e to the iqx. That is e to the px. What is e to the iqx? Using the Euler's formula, cosine qx plus I sine qx. Then the second one, e to the px, I have a minus sign, so cosine qx minus I sine qx. Okay, and then we just know that y is a solution, y1 is a solution, y2 is a solution. The combination of y1 and y2 is also a solution. So let's see. y1 plus y2 should be also a solution. So here we define that y3 is just y1 plus y2. So this one plus this one, they cancel the imaginary part. We have e to the px cosine qx and y1 minus y2 is also a solution. So the other solution is e to the px sine qx. You can also check if y3 and y4 are linearly independent or not. So here, y3 and y4 are linear independent. You can check your W. The Wronskian test is Q times e to the 2px. Okay, it's not 0. So the general solution is y of x equals c1 e to the px cosine qx plus c2 e to the px sine qx. Okay. So in this expression, I only have real valued function, right? And since we have a real value function rather than the complex numbers inside, it is easier to graph. Easier for graphing and computing. Computing the values of solution. Okay. Any questions?
For the y1 minus y2, why isn't it like 2i?
Oh yeah, divide by I.
Divided by I?
Yeah. I don't want I, right? y1 minus y2. We have e to the px sine 2i e to the px sine qx. Right. This one minus this. And I divide by I. And I don't care about this the multiple term.
So it's not y1 minus y2, but y1 minus y2 over I?
Yeah. But-
Okay.
But normally we just say, well, if you plus these two, you get the real expression, and if you divide by this two, well, subtract these two two solutions, you will also get another real expression. Okay, and we use this two.
Okay, thank you.
So here is the summary. So the solution is either two different exponential or same exponential, but the second one at times x. Or for the complex roots, then we have exponential times cosine and exponential times sine. Okay. Now, for example, y double prime plus 9y equals 0. And this time I give you the initial conditions, which means that they can define your constants. So the characteristic function for this differential equation is lambda squared plus 9 lambda equals 0. And your lambda is either 3i or minus 3i. In this case, since it is a complex number, then my solution is, and here e to the px, what is p? Let's see. Actually, you don't have p, right? P is like the coefficients for y prime. So p is 0. That means exponential of 0x, there'll be 1. So I only have cosine 3x and sine 3x. So to determine C1 and C2, we use the initial condition. First, we get cosine, C1 cosine pi plus C2 sine pi equals 1. Then you'll get C1 is minus 1. And another initial condition, we have 3 sine pi plus 3 C2 cosine pi. That's minus 3 C2. That equals minus 2. So C2 is 2/3. And then your y, the solution is minus cosine 3x plus 2/3 sine 3x. Okay, and we have plenty of the drills that you can practice. Okay, first find the characteristic equation and determine they have a different two exponentials as your solutions, or one exponential but the other one is x times this exponential, or you have the exponential times cosine and also sine. Okay, only these three